Welcome to the Grid Mod Pod, brought to you by AEIC. In this podcast, you'll hear from the utility industry's top operations leaders on how their companies are working to modernize and improve our ever-evolving power grid. Thanks for joining us.
Hello, and welcome to the Grid Mod Pod, the podcast that explores the exciting world of grid modernization. I'm your host, Dr. Elizabeth Cook, and joining me again is my co-host, Brett Ryhal.
Liz, thanks for having me back. So I'm Brett Ryhal from the Electric Grid Infrastructure Systems of Sargent Lundy, one of their program managers. As usual, it's always nice to be to hear your voice and to be chatting again with you, Liz. What are we chatting about today?
Well, just for our listeners, this podcast is really for anyone interested in understanding how our energy grid is transforming to really meet the needs of the future. And something that is continuously being spoken of in all facets of our industry is battery energy storage solutions, BESS, or batteries, or energy storage. Many words to it. So I think it would be an exciting topic really for us to dive into really what are the use cases, what is all the hype and innovation about, and really where can we see this new technology and capability of the power grid as we move into the future. So what do you think about that?
Okay, that's a good one. So do have quite a bit of experience with BESS, or battery energy storage systems or solutions. There's many ways to store electricity as there are flavors of ice cream at your local ice cream shop. So the best way to think of battery energy storage is to take a step, I think, away from thinking of it as your AA batteries or lithium ion that's in your phones, or the larger lithium ions that you've seen on some of the commercial scale, and think of it as a way we can store potential energy. One of the ways we've done that in the past is through hydrogen storage. So if you have a hydro facility and you don't need the electricity during the time of demand, they reverse the flow of the pumps, and they pump the water up to a storage facility high up on one of the hills. And when you do need that energy, you open the valves and you release that water back down into the hydro dam, and you can pull electricity from it. Think of batteries, I think, in that term, a way to store energy that we're not currently using and pull it off the grid. So right now on the grid, we operate different types of power plants, to use a simplistic term. So whether that's nuclear, coal, oil, hydrogen, or hydro, and we run those at peak efficiency. And if we use the electricity, great. If we don't, we don't. So there's efficiency losses in that. Battery energy storage is one way to mitigate some of those efficiency losses. So go ahead.
I just can't help myself, because one passion of mine is the history of the grid. So I guess I just want to share a little perspective to our listeners to relate what you're talking about. So at the time of when the grid became a reality, which it all started from enabling and understanding how to create the flow of electrons, which is in essence electricity. And so this happened in the late 1800s, right? And the technology, the machinery, the way to actually make a piece of equipment that could convert a certain amount of energy into a different kind of energy was electromagnetic induction, right? So spinning a massive machine within a magnet, which then pulled the electrons off and sent them on their way. And so just when we think about what you were sharing is the pump storage, the essence of storing energy for use at another time would have fundamentally transformed how we do everything. It is literally the Achilles heel. And so a lot of the work at the time of when we were about to scale to the largest machine we now know, that took 70 years to build, was trying to figure out how to store that energy in a safe way and using the technology and the materials and the science that we had 140 years ago. And so where we are today with all of these different types that you're going to kind of lead us down, it's paramount to really realize that we would be operating and creating a brand new way of building a grid if we had the ability to store energy in the ways that we can store it now. And so now it's trying to figure out how to take this reality and put it into an existing infrastructure. And then while doing that, transforming it to that new reality that, may have looked a lot different 100 years ago. So I guess I had to share, because the idea of energy storage has always been a desire. It's just now that we've found all the ways to do so. So which is the best technology, right? What innovation in a nutshell is really what's happening across all elements of our industry. So I guess I'll throw that to you.
Yeah, you mentioned that to the Achilles heel. So you have solar right now and wind on the grid. It would be really nice if our peak demand on the distribution transmission grid matched up with the peak wind production and the peak solar production of the midday. But that's not really the case, right? So we use battery energy storage systems to capture what we've produced and what we've yielded from those solutions, from those energy solutions, and in a way to store it in a way we can use it later when we do have those peak demands. So we think a lot of times on battery energy storage, we think of lithium-ion batteries. You can see they can be they're the size of like a shipping container on the commercial side for the transmission products, and you can install as much of it as you want pretty much in some areas of the country. When we're thinking on the DER side, the DER side, now we're starting to be able to integrate this now into the distribution grid. So there are other solutions that are available. We have solid state batteries now that are starting to become popular. One of my personal favorites that I spend a lot of time investing time in is a flow battery, which is a way to use an electrolyte solution to during the time when you're trying to store energy, you charge two different electrolyte solutions in two different tanks, and then when you need that energy, you just reverse the pump, and it transfers the energy back onto the grid. So there's even a hydrogen storage is starting to become more popular, and that's why I kind of stuttered a little bit earlier about hydro versus hydrogen. I mean hydroelectric dams. This is hydrogen as in the hydrogen element storage, the ionization of hydrogen. And that's a way to utilize the electricity when we have it and we're not during low demand times. We can create hydrogen and then use it as a safe and reliable source of storage during peak demand times. So there's lots of solutions right now for the grid that are scalable for transmission on the transmission side. And there's also a lot of these that are scalable for the distribution side.
Because I like to create visuals for people and break it down. So when we're thinking about, those that, the power grid itself, I believe should be spoken of it's one holistic machine, but four major components for where we are today. Bulk generation, the energy source that we used predominantly at the beginning of the 1880s onward, was tapping into the fossil fuels, creating a heat of some sort, boiling water, creating steam, spinning machine, sending electrons off onto the transmission grid. Transmission grid is really a voltage level that is large enough or high enough. And what's voltage? The pressure from which electrons are being moved through the assets. High enough so that it can be propagated across long distances. And then tap into the distribution, your third component, which is now predominantly a single-phased system that needs to remain balanced, but predominantly it's very challenging to balance it. And to ensure that the voltage at that step down from transmission distribution is strong and healthy all the way into the customer, which is your fourth component. So when we think about energy storage and what it is, it can truly play a part in the bulk generation, because we have now been able to scale it and size it to bulk 100 megawatt, 200, 400 megawatt energy storage systems. It can play a role in the transmission grid to stabilize, right? And we can talk about all those use cases. But it also has a very dynamic new role in the distribution grid. And then lastly, in the customer behind the meter. So here's a solution, a technology that, if you think about it, is impacting all four components of this massive machine. And so each one technically has very unique dynamic use cases. So it's very hard and broad, right? Like to just say one particular technology is good or bad, because we have to realize where we're talking about it, why we're talking about it, and what it could ultimately do. So all of the different sources and technology you just spoke of can really play in all different aspects of how the grid performs. So I
Yeah.
couldn't.
So what
Oh,
are we
I
really?
forgot about
What
my
are we really?
visual.
Oh,
Sorry. It's the lake. So, right, to maintain voltage stability is to maintain a flat, level. And so you inject electrons and you pull electrons, and 24/7. So when you said like generations dispatched, it's going to be used. And that's what we plan for, because we use the exact amount of electrons that are being produced. But in this new energy storage solution world, that is completely changed. Now we're looking at our
yeah.
tide levels very dynamically different.
Yeah, and what you're really trying to do, in a perfect world with a infinite spectrum of technology, you would have no transmission lines, no distribution lines. Every house would have a 0 point energy source that produced exactly the amount of power they needed at the exact moment at the exact time.
Net zero.
Obviously, probably in our lifetimes, we're not going to get there, Liz. Probably in our
But you
lifetime,
have to have
maybe.
goals and a North
But we have
Star.
tools. But but sci-fi 101s, Star Trek Enterprise, etc. aside, we're trying to head towards the solutions that support that it doesn't need to be, the battery energy storage doesn't need to be sitting next to a power plant. It doesn't necessarily need to be sitting just right next to a wind farm or a solar farm. Now we can push these solutions because of the feasibility of them, because of the size and their density. Now we can start pushing them towards the distribution grid and supporting voltage irregularities and frequency irregularities. You can support outages. You have a poor performing distribution circuit that could cost a lot of resources and finances to upgrade that. And when you're really only worried about possibly 1 or 2 moments in a year where they're having poor reliability or a voltage frequency issue. So now we can start pushing some of these storage solutions onto the distribution grid where they can support the customer directly, improving reliability, improving customer satisfaction. You can push them now into the distribution grid to support their needs during loss of power or during voltage irregularities, under voltage issues. So these solutions can really help support on the distribution side. They shouldn't just be viewed, like you said, just from a power generation, from the bulk power generation. They need to start to be being viewed on the distribution support and the customer side support of the grid.
So I guess, from your experience and just, knowledge of implementing some of these projects, what do you believe, and I think you talked a little about flow, but, most promising energy storage methods and maybe some particular use cases, like let's get into the granular details so that people kind of understand of how a particular energy storage system enabled additional new grid technologies, right? So I feel like it's an enabler, right? So like what is a project that you've kind of saw that proof of concept play out?
Yeah, without giving away too many details, I think viewing things from a microgrid perspective, and by microgrid I mean a
That's a whole
cell
other
phone
episode. What is a microgrid?
microgrid.
Go.
Yeah, plug done. So from a microgrid perspective, a grid that has some sort of self-sustainability, whether it's redundant sources, we've seen some very good use cases on the distribution side of plugging in battery energy storage, mainly right now on the lithium side. A little bit of there's been some interest in flow batteries about plugging these in so that during peak demand times, blackouts, or high usage for EV charging, you don't need to upgrade the entire grid to support once or twice a year 5 minute 5 minute blackout. You don't need to upgrade the entire grid to support EV charging during the very peak demand of when everybody gets to work and everybody's charging their car at the same time and the big current inrush happens. You don't need to have these major upgrades for that. You can actually implement BESS non-wire solutions to support those peak demand cases. or those blackout cases, especially with sensitive electric needs, be it their servers, be it scientific equipment, where they really can't have these voltage fluctuations that we see sometimes on our distribution grid. The power has to be cleaner in a sense. It has to be more reliable. So before you go rebuild and spend 10, 20, $30 million to rebuild a grid, possibly using a BESS and after you analyze the distribution system, using a BESS to support those industry needs or those EV charging needs, or V to X or V to G, can be very, very supportive. After all, if you are having, for example, the EV situation where it's a V to X, having, for example, a fleet of buses that have EV, you don't need them the second they connect back to the station. Sometimes you're using them as a BESS for peak demand needs, where you do have a voltage sag in the system, and you can dispatch them using Durham's solutions to kind of support the grid when it's actually in need of that power.
I feel like this episode's going into Professor Cook, but when we talk about
this is kind of your highlighted topic. I should be asking you the questions on this one.
Well, no, you're providing the use cases, but I think from our listeners' perspective, like energy storage, why can't we just put batteries everywhere, right? And just giving some of those fundamental, awareness or those aha. So what is voltage, right? Not getting into, sinusoidal math here, but voltage is a mathematical term that we thought up in 1840 or maybe 1860, George Simon Ohm's law. So voltage equals the current, which is the flow of electrons, times the resistance. And so we've developed a system that's asynchronous, so it's alternating current. So now you're introducing imaginary math. So when you think about power quality and ensuring that our customers, the commercial and industrial, have very sensitive loads, it is paramount that the amount of imaginary power, which is VAR, is not detrimenting the overall real power. So without getting to the math, is kind of like, and I used this today with one of my lawyers, so I'm going to use it now, is when you think about root beer, the root beer in itself is your real power. The foam that, you need to have the foam to have good quality root beer is like your VAR. So if you don't have any, you have poor root beer. If you have too much, you have poor root beer. So you got to create that balance. So when you're talking about power quality and ensuring, the VARs and the watts need to really work themselves out. And when you have this intermittent type of energy source that's coming from, say, solar or EVs charging and discharging into the grid, having that ability to kind of smooth out that interaction is what a very valuable use case. And so I think you're talking a lot to that, but to some of our listeners that aren't electrical engineers, those are the intricacies and the challenges that really make each of these solutions, unique in themselves. So there you go. Professor Cook's taking the hat off.
as you're having those peak demand, and really what we're talking about peak demand is high current demand, right? On load demand. So if you can imagine if you have an arc welding facility or a steel plant that's sitting next to an apartment complex in our imaginary situation, and they start churning out product, you're going to have these high energy demands, these high current demands that can cause a voltage sag. And if you had customers in an apartment complex that are noticing these voltage sags, whether it's flickers in the lights, their LED TVs not turning on, their computers possibly turning off, that becomes a very big nuisance issue. And I think for a lot of utilities, for a while, it's rebuild an entire distribution system, add a new transformer at the substation, add new relaying to protect the transformer, new bus,
a little bit corrective capacitor banks.
Yeah, a huge upgrade for what may only be small intermittent loads that are happening. Sometimes they're happening a couple times a month, sometimes they're happening daily, that can lead to a customer dissatisfaction that's not beneficial, definitely can give you a black eye, when you could possibly put a battery energy storage or capacitive solution near those peak energy demands that could support it and in essence, resolve the issue. I think one of the cases that we worked on together was an intermittent outage issue. So it's not necessarily always voltage. It's sometimes supplying for intermittent outage for a residential area for residential customers. And the battery energy storage was really only meant, it didn't have to be massive. It was only meant to supply power for, a couple minutes, right? So, there are some cases for this where you can really, really support customers during those peak demand times.
Right. So it's like not just using it as an energy source or playing into a market. We're literally just using it to increase reliability as a non-wire solution. That's the use case we're talking about. Yeah. So I think, very broad topic again, but a very nice sample of the world of battery energy storage systems, that's another fact, right? Before we wrap it up, there's the battery itself. So the chemistry thereof, it's unique, and there's really hundreds of variations that are like being studied and tried to understood. And then a part of the storage system is how to encase it, how to control the heat, to take that energy and convert it, how to protect it, how to store it. So there's it's a battery integration project, which is a lot of unknowns. But with that, kind of what I heard, in summary is they can ultimately play, and they will play, a pivotal role in how we're going to integrate all of these other new technologies. It's a technology that enables others.
It should be leveraged. It definitely is something that we can leverage on the distribution systems, not just on the bulk generation side, but on the distribution systems to really support the energy demand needs of the end consumer.
Yeah. So provide grid stability, really help reduce and enable proliferation of EV charging, and then create this flexibility as we roll out and prepare the grid for increased electrification. So battery energy storage has a place, and I think the innovation and everything that's happening around it is very exciting, and I look forward to continuing this conversation as we talk about everything grid mod.
Yep. Appreciate it once again having me on, Liz. We could have probably dove into this once again for an hour, but wanted to hit the highlights of it. So if you have any questions, feel free to leave a comment, and we'd like to address them more.
That's a wrap for this week's episode of the Grid Mod Pod. Thanks for tuning in. We hope today's conversation got you thinking about new and creative ways to improve our power grid. Be sure to subscribe to our YouTube channel to be the first to hear new episodes. This podcast is brought to you by AEIC, the place where operations leaders come together to share knowledge and provide guidance to the electric utility industry. We'll be back with a new episode soon. Until then, keep powering on.